It's a great pleasure to introduce Maryna Viazovska, who needs no introduction. This is already a third lecture, and she will continue this wonderful series on Fourier interpolation.
Thank you very much. So, I will start by recalling where we stopped last time. And so last time, what we stopped the Fourier interpolation formula and how it is, how to derive it, how to obtain explicit formulas or some formulas for the interpolating basis. So this was the Fourier interpolation formula. So that looks like this, that we claim that there exists some sequence of Schwarz functions. And last time we spoke about the functions on the real line and then about even functions on the real line. But today, maybe let's make it a bit more general and let's speak about Schwarz functions in Euclidean, in D-dimensional Euclidean space. And to make our life a bit easier, let's consider only radial Schwarz functions. So radial, it means that the value of function depends only on the point depends only on the distance from point. Example of radial function.
So it's bien in both cases, bien and bien.
Okay, thank you. Yeah, these are two different sets of functions, and so we want this sequence of this would be our interpolating basis, and what condition that we want to be true is that for any function f, the following should be true. So the value of function f at any point x can be computed by the following way. And so this should be true for any point in the Euclidean space. And so by now we know actually several other variations of similar interpolation formulas. For example, a formula with where instead of considering values of functions at square roots of all integers, we can consider values and derivatives of function at square roots of even integers. And there is also an example, I think, which is still not completely written down, where we have two arithmetic sequences with sort of gap 2, but with a shift. So this is a result of Danilo-Radchenko, where he could also prove a similar formula. And then this second degree interpolation would be as a limiting case of formulas like this. But somehow this is the easiest case, so maybe let me first explain the easiest case and then to speak about a bit about how this could be extended or whether it could be extended.
Will you want n0 equal 0?
So actually, okay, so as dimension grows, it turns out that we can start our sequence later. That's like this n0 and n0 tilde, they will depend essentially on the dimension. And as we have seen in dimension 1, we can start from 0. Actually, if in dimension 1, if we consider even functions, we can start from 1 And then because if we know all values of even function except for point 0, then we can use Poisson summation formula and recover value at 0. So we can skip the value at 0. And it turns out that for odd functions, actually, only the values is not enough. We also need to know the value of derivative at 0. And yeah, so, and well, this is what I already done last time. So one trick that I'm using here is that I consider the generating series. We are introducing a new variable tau, and it will be a complex number with a positive imaginary part. So it's in the upper half plane. And then we consider a function like this. And so now what we do, so then now if the interpolation formula is true, then what we would know about this function is that, okay, so here it's a bit of, I wanted to have, I wanted to have two functions. Okay, yes. And now, so now what happens is now that these two functions, they satisfy a functional equation.
So you assume you have a formula like what you want and you
Yes,
use things.
yes. And so how it works now, we assume that interpolation formula is true for the complex Gaussian function with parameter tau. So we assume this interpolation formula for f tau of x to be e to I squared tau. And so if tau is in the upper half plane, then this would be indeed the Schwarz function. And from here we can see the following functional equation. And the functional equation will be that e to the I squared tau equals to f of x tau plus f tilde multiplied by this automorphic factor of -1/tau. And this is true because the Fourier transform acts nicely on Gaussians. And we know exactly how it works. So, but then together with, so this is one equation that we can get, but also what we know from the very shape of the generating series. We know the generating series, they are two periodic in tau variable. and F tilde is also two periodic.
What is the exponent? Just minus I tau on the right in the functional equation.
Maybe write the functional equation on the next board because I think that people can't see it.
Okay. Okay, let's begin with this first think about dimension. And so now it turns out that this is an equation we can actually solve explicitly, and there are methods how to solve that. And so why is it like this? It is because if we let's consider a slightly different functional equation. So let's maybe from solving functional equations, we know that sometimes it's useful to make an equation homogeneous. So for example, let's forget about this part. Let's pretend that it is zero. So let's look at the equation like this. And also if you forget about this part, let's also forget about x. Because like what relates somehow x to our f is this part. So if it is gone, then x is also gone. And so we get an equation like this. And so, okay, so now let us look at this at the upper half plane. And so if we look at the tau at the upper half plane, then 0, -1, 1. So we see that this equation, it simply means that H is two periodic. It means that function in this strip looks exactly the same as it is in this half strip. It looks exactly as it is in this half strip. And somehow what this equation means is that our function is essentially up to sign symmetric with respect to the inversion in the upper half plane. So it has symmetry with respect to this action on the upper half plane. And so then a periodicity of H tilde, it can be translated into a symmetry of H under another linear fractional transformation, the linear fractional transformation that leaves 0 unmoved and then somehow moves our, so it is a bit like translation here, only if the cusp at 0 is mapped to cusp at infinity. And so here very nice things happens is that these two transformations, the linear fractional action by tau goes tau plus 2 and tau goes to I think like this. So the action by this matrix and linear fractional action by this matrix, they generate a discrete subgroup of SL2R. And and this condition for H, it simply means that H is a modular form for the group gamma 2. So this group.
Discrete is obvious, you can find
Yes. Yeah, it is a subgroup of SL2R, and it is, I think it's index 6 in SL to this. So, so then we consider this group. And it's also true that this group is actually it's a free group generated by these two matrices, which is also important for our story. And so it is important because now, because it's a free group, it makes the solution of inhomogeneous equation easy. It means that the solution exists. Actually, the solution would exist for essentially for any function that we put here. So here we put Gaussians because they're convenient for us, but here we could put any reasonable function of tau, and we would also get a solution. And because this is a free group generated by these two elements, it somehow means that we have no abstractions for solving this equation, no additional conditions on the function in here. And so probably now this is on one hand, this seems like a nice story, everything works. So now we could actually write down the solution after some finite amount of computation. On the other hand, it seems like seeing this discrete subgroup in the background, it's something rather special. So, and if we want to somehow think of this interpolating formula as some analytic phenomena, then if we perturb our nodes a little bit, then this story would be lost. So then it has to be replaced by something else, which I don't know what that should be. And so when we are in this good situation, when everything works nicely, so then we have actually we have concrete, rather practical methods how to solve this equation. So have explicit methods to solve the equation. And I say methods because I know at least two that look, they're connected to each other, but still quite different. And so the first method is by using contour integration.
For the homogeneous equation, we will get finitely many solutions.
Yeah, finitely many for this one, yes.
Yes.
Yes, and yeah, and but for this solution, we will get our unique solution, of course. But then so here what I did not write on the blackboard yet is that here we have to be, if we want a unique solution, we have to be careful with our choice of n0 and n0 tilde, because if n0 and n0 tilde are not zero, then it actually puts also finitely many conditions on our function f. And if we put sufficiently many conditions so that they somehow would exclude this the actual holomorphic modular forms, then we will have a unique solution. And so second method, which I would like to talk about today, is by using Poincare-like series. So we can.
Let me ask a question. If you were to take other sequences in the group, you would get a subgroup of SL2 orbiter would not be discrete.
That's it doesn't need to be discrete, and also somehow if I have other sequences, if for example if these roots have absolutely no structure, then it's even somehow just we want to have a series with prescribed, like for example it's with prescribed expansion by prescribed exponents, but then it will not easily translate into any transformation properties. And so we know somehow the Poincare series are actually used to construct modular forms of sufficiently high weight, and a similar technique also can be used to construct solutions of this equation if dimension is big enough. For example, it has to be bigger than 4. If it's bigger than 4, then we have convergence. So, and so let me start a little bit with a contour integration. So how does that work? And so here it's, I think it's something that existed already for a long time. Probably the inspiration comes from solving boundary problems in differential equations, ordinary differential equations. So here is many things already worked out. We just have to use to take what exists and use it wisely. And so here we suppose that K, and we are again so that the usual recipe to solve problems like this is again to try to find a solution to the homogeneous equation. Only instead of searching for holomorphic solutions, we will search for meromorphic solutions. K and K tilde are meromorphic functions. Okay, so another thing is that they are functions of two variables, and so variables tau and variable z. And then if you look at this function as a function of first variable, then they should satisfy this homogeneous functional equation. Meromorphic function satisfies this equation, and also want to have some more information about the poles of the possible poles of this function. And so second condition would be that the poles of K tau z for so here now tau is fixed and z is considered as a variable. And we want them to be only simple poles. at the points. So we will have poles only at the gamma 2 translates of tau. So Z, only if Z is a gamma 2 translate of tau, only in that case we are allowed to have a pole. And also what we want the residue of Z equals to tau of this kernel to be 1.
Transformation properties for GAN, for Z.
Yes, and then somehow transformation for properties for Z, if we put more conditions on somehow on the growth of this kernel of Z, then they could be deduced from these conditions, and also what should be the residue in other. So I told you what is the residue as Z is equals to tau, and at other gamma translates it would be essentially the meromorphic factor which comes from this equation.
When you see a residue, you multiply by dz to have a one form instead of a function.
Yes. Yes, here when I write residue, I mean the way we studied complex numbers class of the integral around the pole.
Excuse me, just thinking of the tau dependence, if you have k and k tilde, isn't that a little more complicated than an ordinary modular form? Because you've got two.
Sorry?
It's not quite a modular form, right? It's a vector valued one or something like that.
Not actually, in this case, it's an honest modular form. Like for simple roots, it's an honest modular form, and everything is easy.
I just meant in general with k and k tilde, you have two sets of functions, so to speak.
Yeah, but it is okay. So here there are two functions, but then somehow like this equation means that just k tilde is just essentially minus k. So okay, so this so k tilde is just this slash operator for the inversion applied to k. So it's somehow a trivial. One can take usual modular form and can look at its expansions near cusps and then say that it's a vector valued modular form. But and the question is it a useful way to? Sometimes it is a useful way to look at it, but.
Do you impose growth conditions for to go into infinity?
Yes. So there should be also some growth conditions here to make this unique. But I will not probably get into those. And so after we have defined our and actually we have here we are because we have an explicit very explicit formulas for the in this case, in the case of a simple interpolation formula, we have a very explicit formula which actually works in different dimensions, so with a sufficient amount of degrees of freedom. So this was in the case of dimension is 1. This is my joint paper with Daniel Orechenko from 2017. And for other dimensions, and here actually it turns out that the dimension does not even have to be an integer. So it can be actually a real number. And the only difference here, of course, then we do not speak about Fourier transform anymore. We speak about Hankel transform. And this the kernel I'm going to write now. It was computed by my PhD student Martin Stoller in his PhD thesis. And so what he suggested to do is to he fixes D. And also considers two integer numbers L and L tilde. And then what we can do is to consider a kernel like this. Maybe I will skip the normalization. So we take a modular lambda function. So modular lambda function, it's a function of the upper half plane, and it is a modular form of weight 0 with respect to gamma 2, and particular also. Of course, it's not unique, but it is a helped module. So in the sense that it generates all. If we consider a field of functions generated by lambda functions, it will generate all weight 0 modular forms for gamma 2, and then it's normalized in a particular way. So it has particular valuations at the cusps of the group gamma 2 at 0, infinity, and cusp 1. And so this is somehow.
Lambda prime will be a form of weight 2.
Yes, yes. So this would be a form of weight 2, and then we divide it by the difference. And so now we take a usual theta function and raise it to the power d. And here, because d is, we took d to be not an integer, so here it also has to really specify what this means. So theta function, it has no zeros at the upper half plane, so it makes our task a bit easier, but still we have to make some choices. So usually my favorite choice is to take this, to look at the theta function, the imaginary axis, and to take their some usual branch of this power of a real number.
Be clear, that's just theta of tau, right?
Sorry?
Theta of tau, right?
Yeah, theta of tau, and then it's so we have to watch what the weight would be like. So it is divided by theta of z, and then here we have one more term which will regulate the behavior of our form at all the three cusps. And so now the choice of L and L tilde, it will be connected to the choice of N0 and N0 tilde. And yeah, so now how, after we have fixed one of these kernels and we have chosen L and L tilde in a correct way or in an admissible way, then we can solve the equation there.
It's a product function times the only dependence, which is not a product, is lambda z minus lambda tau, if I'm reading. Yeah, okay.
Okay, so I made me. Okay, probably this should be. Yeah, so this term, it somehow regulates the weight of the function, and so this is always some function of tau divided by function of z, so that our residue condition is still true. And so then we define our function in the following way. So here we choose a contour gamma tau, and we take one of our kernels. And so this would define our function f for, if you take this, consider this fundamental domain of be a fundamental domain for the action of gamma 2 on the upper half plane. So these all the its intersection of this half strip and its image under the inversion at the upper half plane. That's usually a convenient fundamental domain for gamma 2. And so this will be true if tau is in the fundamental in this domain, and also the gamma tau here. How do we choose it? We choose it in the following way. So if we take our tau in the domain D, and then we will choose gamma tau so that it starts at -1 and ends at 1. And also we choose our gamma tau so that tau is above the gamma tau. For example, if our tau was here somehow near this cusp at 0, then we would take the path gamma tau to be lower. And also because D is a fundamental domain for gamma 2, we see that all other poles of our kernel, they are all somehow either here or here. So this is the only pole of our kernel in the domain, in the set D. And so now what the next thing which we do, so we have defined our function for tau in D, but then we also want to define it from the all upper half plane. And here what happens is that we can actually continue this function holomorphically to the whole upper half plane. And as we continue it to the all upper half plane, so here it would happen that somehow our point tau and the path gamma tau, they might actually collide. And this is when we will, this is how we will get this non-homogeneous part of our equation. And so now what this method does for us, it also allows us to compute. So now we have an explicit formula for the whole function f. And we can also now find explicit formulas for the basis functions Bn. So here now this happens more or less in a formal way. So if
is it obvious it's Schwartz?
So it will give us to work a little bit, because somehow here we have the Gaussian, it's nice, and we have this kernel, and we have chosen kernel so that it vanishes near to as z goes to -1 and 1. But then there is still some work to be done, because somehow as z goes to the real line, of course, then Schwarzness is challenged. So it's important that we have vanishing here, and that is still a Schwarz function. Okay, so now if the imaginary part of Z is bigger than the imaginary part of tau, then what we can, okay, or maybe let me think. Oh, probably it's imaginary part of tau has to be bigger than imaginary part of Z. And we look at our periodic meromorphic kernel. So it's a periodic function and now in tau, and now we can write down its Fourier expansion and it will converge under this condition. So we can write our kernel. And here we have what we have done. We have chosen this additional parameters L and L tilde, so that the Fourier expansion of our kernel will start from this from the number n0, and so we will get some coefficients, Fourier coefficients which depend on Z times e to the and now what we do, we can just substitute this expansion into our formula for f and formally compute what Bn is. And so again, gamma would be a path from -1 to 1. And so the functions Gn would be a weakly holomorphic modular forms of weight 2 minus d over 2. So, and so this is an explicit formula for our basis functions. And also from this representation, it's actually possible to see that this interpolating basis, it's also this free interpolation basis, so that the values of Bn at square root of m is exactly what we expect them to be. So and so now let me also tell you about a different method and another way how to construct the basis vectors. And I think that method, it still depends on the existence of this discrete subgroup. However, it seems to be a bit closer to analysis, and maybe that one is more promising if someone wants to generalize this also to other sequences. And so let me speak about the Poincare-like series.
Just one question.
Oh, yes.
The construction of K there, I know more or less nothing about the field, but it looks totally miraculous. Is there some intuition like?
Yes, so somehow. Yeah, so intuition, maybe some intuition can come from similar problems in differential equations where the existence and uniqueness of kernels with similar properties is proven. But then this, I think, also because of like gamma 2 and because it's such the subject that was studied for a very, very long time. Here we already know what the answers are. So. And also this is because of this also happens because of the modularity properties, because we know really a lot about modular forms. And for example, here we know that all these functions like lambda and theta, they do have the transformation properties with respect to the group gamma 2, and at least how I look at it. So the we believe in existence and uniqueness, and we have all these classical modular functions, then we can construct something which seems like like it has the properties we need, and then we check it and see that it actually works.
You wrote that D can be positive or equal to 0. What are
Maybe let me get maybe I'll write here 1. So sorry. But actually, when D is equal to 0, in some sense, this like the problem for F, that's actually exactly something we have done together with Hakan Hedemalm. Then this problem, it really becomes like a very classical boundary condition problem. So then there is no this modularity, and we just need to construct a function with certain jumps on this around these circles, or certain behavior on the so that and actually things become even in the if dimension is 0, then things even become easier.
What is the Hankel transform?
Sorry?
What is the Hankel transform from D equal to 0?
I think it is I think you just take a Bessel function of corresponding with corresponding index, and as I remember, it is well defined, so it's not a okay, so let me switch to the point correct series. So maybe and so this is also a result which Martin Stoner obtained at his PhD thesis. Here, as you know, the usual Poincare series, they are defined in the following way. So, for example, if we let's take D to be, maybe let's first do some notation. It will be convenient to use the slash operator. So it would be, we have f, which is the function of the upper half plane, and we have a matrix in Z. Then we can define and maybe also for us it probably can be a real number. So this is the usual weight k. This is the usual definition of the slash operator, which helps working with this modular invariance of weight k. And in our case, we want to go a little bit beyond the classical definition, and we do want k to take real values, and also the automorphic factor, it will be automorphic factor related to some multiplier system, so it will be a bit more complicated than this. But since I don't have much time left, maybe I will skip those more fine details of the definition. And so maybe I would say that maybe one important property of the slash operator, that it is an action, so that if you have fk and you have product of two matrices, and it would be the same. This is an important, convenient property of this notation. And so now the usual Poincare series, they are defined in the following way. So we take a function, so it's we want to construct a function which is invariant under the action of a group. It's natural to consider the averaging over the group. And as our group is infinite, many things can go wrong, of course. So one method which proved to be working is that let's take, so we know that this shift by 2 belongs to our group gamma 2. So our modular form will be two periodic functions. So let's take a function which is already two periodic. And then there's the classical Poincare series are defined in the following way. So we would fix some integer m, and we will take a two periodic following two periodic function. And now we will average it under, not exactly average, but take a sum over actions of all elements of gamma 2. But of course, we know that if if an element in gamma 2 is in a group generated by this element, then somehow it will not change our function. And so if you will want our sum to be finite, then what we do, we would take a group generated by the subgroup generated by this shift, so it's denoted by gamma infinity because it's so this is a subgroup of gamma 2 which fixes the cusp at infinity, and we look at the sum like this. And here we take this, we apply the slash operator for an element here. Maybe gamma, let's make this gamma, I will use it for a path. And it turns out that if k is big enough, so if k has to be bigger than 2, then this series would converge, and this would be the so-called Poincare series. And so one thing that so Poincare series, they can be, we can use this summation, and then if convergence is fine, then it allows us to construct solutions, essentially solutions to this homogeneous equation here. And so now one thing that we can do, we can try to use similar ideas to construct a solution to the non-homogeneous equation. And so here the idea is also to take a sum over certain elements of our group, only to choose these elements in such a way that this non-homogeneous functional equation is formally true. And so now the idea would be find two subsets of our group such that the following will be formally true, so that the okay, so now we look at this equation as an equation in a completion of a group algebra. So we take our identity element. Let me write it in square brackets, just avoid the confusions. So this should be the sum over all elements in B. Okay, so here I want it to be of course, this would be always true for this would be always true for all sets B. So this is just somehow, here it's only the question of convergence, which we try to forget about for a moment. And so now what we also want to be true, we want to be the following to be true. We want at least formally to have the following condition, that if we take our set B and multiply it by this element here, this has to be B back. And then if we take this identity minus B and then multiply it by the evolution and then multiply it again by the translation, then this also has to be this element here again.
I don't understand what you mean by identity.
Yeah, so I think of this as a just formal sum of elements in the group. And then somehow, if we can find a subset like this, then what we could define down. Maybe let's call it different. Let's call it first it will be G. So this will be we're applying slash operator, and we apply it to M. And for G tilde, we do a similar thing. This would be sum over And so so now what this set B should be to make the whole trick work. So then the set B has to be the following thing. So so we know that. So let's make a notation. Let's denote this matrix by A, and this matrix by B. And we know that gamma 2 is a free group generated by A and B. And so for each element of gamma 2, it can be written as a reduced word in A and B and their inverse powers. So now we will define the set B to be the following set. So the set of all elements M in gamma 2, such that the reduced word for M, it starts with a non-zero power of B. And then it becomes already not a difficult exercise to see that then this
Lowercase b?
okay, this is lowercase b, right? Then this property, then function is defined in this way, they will actually solve the non-homogeneous equation, at least formally. And then if the dimension D is big enough, then this sum will in fact converge and it will define a nice holomorphic function in the upper half plane.
Where did X disappear?
So X is here in this story. So it's in the function which we have applied to. And here's another interesting thing: if it happens that the absolute, so the length of x squared is an integer, then this function here g, it essentially becomes the classical Poincare series. I think it would be classical Poincare series minus e to the pi I m tau. And another interesting thing is that the solutions we have constructed in this way, they will not coincide with the solutions we have constructed previously. And so this is true because somehow, of course, these conditions for n0 tilde and n0, they will not be satisfied. So there will be modular forms that will contribute to these functions g and g tilde. So we'll need to still do some work with them to make them, to relate them to our previous solution. Maybe the last thing I can say that it turns out that these solutions G and G tilde, they're not Schwarz functions in X anymore. So at least in those cases when we have non-trivial modular forms, they will not be the Schwarz functions.
And you need big enough also.
Sorry?
And you need to dimension at least 4.
Yes. So also if dimension is small, then the series will not converge to the equation.
Then you could use the analytic continuation of so.
But probably it should work. I don't know. Maybe I don't know. With analytic continuations, there are also sometimes some surprises. So I don't want to claim anything here. So yeah. So but then it seems to me that this maybe this the Poincare series construction, maybe it can somehow help to overcome this restriction that we have from gamma 2. but that's also still very speculative.
I think we have time for a couple of questions. Comments, questions?
Could you tell again which other case you can handle? You were telling two arithmetic progress.
Okay, so one case which was somehow important for the sphere packing problem was when here we have like this. So. When we have when we also have the derivatives, and then this also changes the functional equation in the following way. So it will be instead of having looking at functions which are two periodic, we will have functions which are like linearly one periodic. So it would be function which has period 1 times tau, and another function which is periodic has period 1. And so it turns out that this functional equation does lead to what they asked about the vector valued modular forms. So this equation does lead to, in a more natural way, to a vector valued modular forms and for certain representation of dimension 6. But fortunately for us, it was a representation we could understand very well. And so we also could construct the meromorphic kernel explicitly. So there was a analog of this yellow explicit formula, which was here, only much more complicated, unfortunately. Yeah, and then another case, which I think it was announced by Danilo in a conference in the American Institute of Mathematics some years ago, where he could do things here, like not with derivatives, but with values. And here it would be something like this. So it would be, I think it would be, okay. It's
two
like
parameters shifting.
Yes, like shifting two parameters. So yeah.
Still 2n? Oh, yeah.
Yes, so they had this like, yeah, it was still 2n. So here it's like square root is over everything. Like 2n plus beta, and this is under the square root. Yeah, but somehow this like 2 is important because because it was then it still would be related not to this. So the functional equation would be different, but it would be related again to some vector value space of vector valued modular forms, not with this representation, but with a different representation. But that representation also could somehow be valid. But maybe what is most important is that in the story I told you that a discrete subgroup in the background was gamma 2. If we have this like only one set of shifts, and if we have 2n here, then the subgroup in the background would be SL2Z, which is also a discrete subgroup. And then if you have, for example, want to do something for 3 shifts, then it's already, there is no discrete subgroup. And things just get cut.
It seems to be twice less many values you take.
Probably no, because it's, okay, maybe let me, okay, so that. So like the first story, it was like this. If we have like all just like Okay, so here integers, square root of integers. Then the second story, it was something like this. So there was like 2z, but it was multiplicity 2. And the story of Danilo, it would be like this. It would be like, okay, so maybe here I'm like z, like 2z plus alpha. Together with 2z plus.
Yeah, it's the same.
So the density would be the same, something like this. Here it becomes a bit ugly, but things that look like.
And you take the same bond on the Fourier side and on the general side.
Sorry?
You take this lambda equals lambda tilde.
Okay, here I don't remember all the details because again, and also because it's not even my fault, it's because Danilo did not write down his details.
All right.
But yeah, okay, already maybe he already actually I need to double check. Maybe he already did, and I'm
Yeah,
just
there's another question.
spreading false information.
So just a practical question. So these interpolation basis functions, what do they look like?
So I have them plotted somewhere, and okay, they don't look particularly. They don't look like cardinal sign, for example. They don't look that beautiful. So they look what they supposed to be. So they like, of course, if they have this free interpolation property, that they, for example, take 0 in all our nodes except for 1, and then takes value 1 at that one special node. And visually, what they look like to me a bit like orthogonal polynomials. So in the sense that they satisfy all these properties, but then they also have a lot of oscillations. So
can you localize them in phase space?
Not, I think they do localize, but not that great. They are, I don't know. So I did not actually look at did this kind of computation where I tried to plot them in
We went to the blackboard.
double
Talk,
space. Yes.
so no pictures.
Yeah, but I mean, it looks like they, in a sense, they do localize around that value where they supposed to take value 1, but not as nicely as one might hope for. There are also some kind of noise around that.
They can't because of the uncertainty principle. Right? Because the Fourier side has to be controlled at the same time.
Yes, so they don't look particularly nice. We have some estimates, for example, about how fast they grow, and depending on different parameters that are involved. But
All right. So I think we ready. I think to end the series. So let's thank Maryna for all 3 lectures.